Yay!
Yay! Let's apply, hopefully, a familiar idea from Physics 1, that being potential energy, to charges and electric fields, and let's see what happens. All right, suppose I've got 3 positive charges, and I want to assemble them in a configuration like this. I guess I keep using green for positive, so maybe it's obvious they're positive, but anyway. So I've got 3 charges. Now, if I do this, if I try to bring them some distance r, maybe it's an equilateral triangle, right? So if I bring them some distance r away from each other, you know there is some potential energy stored, right? There is energy stored, and that's what we're going to call the potential energy. And you know it's stored because it's almost like a little spring. If I let one of those things go, it would just fly off to infinity because those charges are repelling each other. So in that arrangement, there's some energy stored that if I let one of them go, I'd get it back out as kinetic energy, let's say. All right, so let's see if we can figure out how much energy is stored. We'll assume that you already know, or that you can look up the formula. We won't derive it. That's like a separate lecture. So the stored energy is going to be equal to the amount of energy it takes to assemble the arrangement. Hopefully that makes sense. If it takes me, 10 joules of energy to get these 3 things that close to each other, then I have stored, if I bring them in from infinity, where they're not interacting with each other, then if it takes me 10 joules to build this thing, then if it's stored energy, I should be able to get that 10 joules right back out again if I let them go. So that's the energy stored is the same amount of energy it takes to assemble this thing. Okay. So what we know is that the potential energy between 2 charges is just equal to k q1 q2 over the distance between 1 and 2. And remember, the cool thing about energies is that there's no components. It's just a number, which is great. So this is in joules. So here's how we do it. There's several different ways to do it. I'll tell you how I do it, and then I'll give you a little bit of a shortcut. What I do is, to assemble this thing, I just play it in my head. How would I assemble this thing? So the first step is just bringing charge 1 in from infinity where there's no other charges around. So just Q1. And if I bring in only Q1, how much energy does that cost me? Nothing. Didn't cost me anything because there's nothing to interact with. Energy is always some sort of an interaction with a system. So if there's just one charge, there's no energy. I can do anything I want. I can move it anywhere I want. Aha. But now, if I bring in charge number 2, there is going to be energy associated with that because I have to get it within a certain distance. Right? They're sort of pushing against each other. So I need to apply some sort of force over some distance, right, from infinity. And so this is going to be K Q1, Q2 over this final distance. All these distances are the same, so I'll just call it R. Okay, there we go. So that'll be the energy required to bring in charge 2. So now I got 2 charges. Now I want to bring in the third charge. So what happens is, remember from before, there was this thing called the superposition principle. And the idea was, for electric fields, we just imagine we can treat each one independently, forget about all the others, and just sort of add up all their contributions. So we do the same thing with energy. So when I bring in charge 3, what it does is it interacts with whatever charges are already there. So I bring in Q3, it interacts with Q1. So I have a K Q1 Q3 over R13, but R in this case. And then it's also interacting with 2. So now I just forget about Q1 and I just interact with 2 like that. If I were to bring in a fourth, then it would be KQ3, Q4, or whatever, right? It's how many ever charges are there is what it interacts with. So each time I bring in a new charge, there's charges that it interacts with that I have to add up. Okay, so the shortcut is, if you look at this, the total U, the total amount of energy stored then is going to be this. It's going to be K Q1 Q2 over, you know what, I'm just going to go ahead and just to make it clear for right now, I'll just put, because maybe it's different, maybe it's some crazy arrangement, and then we'll simplify it in a minute. Plus K Q1 Q3 over R13 plus K Q2 Q3 over R23. Okay, that's the total. It's going to have 3 terms. The shortcut, this is how I always do it, just to be sure. But the shortcut is that you'll notice what it really is it's a sum over pairs. There's 3 distinct pairs of things that interact. 1, 2, 1, 3, and 2, 3. So the shortcut is that you could just write this down from the beginning if you want, just by summing over pairs. So that's, you can do that if you want. It's just kind of more fun in my head to think about building this thing, so I just kind of go one at a time. Okay, so there's something neat that we can get out of this. Let's talk about atomic nuclei. Let's suppose that each Q is a proton. Let's suppose that each of these are protons, and I'm bringing them into some to an equilateral little tiny triangle, like a little nucleus. Forget that if there's supposed to be neutrons there, forget about that. So it's just 3 protons I'm going to bring in to R equals 2. What's a typical nuclear distance? It's a femtometer, 10 to the minus 15 meters. So this is 2 times 10 to the minus 15 meters. So let's bring it in. So my total amount of energy, how much energy would it take to bring these protons in and make a nucleus like this? In other words, what's the energy? What's the available energy in a nucleus like this? It would be, all of those Q's are the same, right? And those R's are the same. So this looks like 3K E squared, the fundamental charge, divided by R. So if I do this, 3K E squared divided by R, what is that going to be? 9 times 10 to the 9th. 1.6 times 10 to the minus 19th squared over 2 times 10 to the minus 15. Not squared, that would be force, right? Energy, it's just R, not R squared. Let's see, so if I do this, let's see what I'm going to get. Let's see, I'm going to have a 1.6 squared, what is that? 2.5 times 3, what is that? 7, 9, 63 over 2. So 3.5. Actually, let me leave that the way it would be. So that'd be something like 35 in the numerator, let's say. And then the powers of 10. I got a 10 to the 9th. And then I got a 10 to the minus 38, so that's what, 10 to the minus 29 on top, 10 to the minus 15 on the bottom, so 10 to the minus 14? So 35 times 10 to the minus 14 joules, right? Energy is in joules. It's useful, by the way. Oh, so anyway, this would be, if I wrote it the right way, this would be 3.5 times 10 to the minus 13 joules. Okay. Anyway, so that's in joules. When you're talking about atomic nuclei, that unit doesn't make much sense, joules. Instead, we use a little tiny unit of energy called an EV. That's the energy you get from accelerating 1 electron, 1 fundamental charge, through 1 volt of potential, which is the unit that we're in. But anyway, it's just a teeny tiny amount of energy, and the conversion is 1.6 times 10 to the minus 19th joules per EV. So it really is tiny. So joules goes away, and I get like, what is that? Just a little over 2.1. Oops. (2.1 times 10 to the 6th, 2.1 mega electron volts, MeV. 2.1 million electron volts. That's how much energy is locked up in this nucleus. So that's also the amount of energy you get if the nucleus disassociates. If you somehow, because in a nucleus, there must be a stronger force. The strong nuclear force is holding these things together. It's got to be a little bit stronger than that repulsion. So if somehow the strong nuclear force were defeated, if you could turn it down to zero, this would be the energy you would get out as kinetic energy of these things when they're really far from each other. So let's just think about if we were to sort of cut these strong force bonds between them, and they could rocket off to infinity. How fast would they be going? Well, we could say far away. What we say is that the amount of kinetic energy that each of the protons would have is just the same as the potential energy of how they're bound together. There's three of them, though, right? So really what happens is that whatever available energy is probably split between the three of them, let's say. So the kinetic energy available is just U over 3. So that's just going to be Ke squared over R. And that's going to be equal to K is just 1/2 mv squared. All right. So solving for V, that means how fast are these things going to be moving? Let's see. V is going to be, 2 Ke squared over m. All right, so we can solve for that. Let's see how fast these things are going to be going. What is that? 9 times 10 to the 9th. E squared 1.6 times 10 to the minus 19th squared. And then the mass of a proton, 1.67 times 10 to the minus 27. If you plug these numbers in, you're going to get like 1.2 times 10 to the 7th meters per second. That's how fast these protons are going to be moving. I mean, that's really fast. That is, what, 5% of the speed of light? Speed of light is 3 times 10 to the 8th, so it's 3% of the speed of light. Anyway, that's really fast. That's also, if you think about it, if that's how fast the protons are going to be moving when they're far away, turning that around, that's also how fast the protons have to be moving in order to get this close together. Let's say you have a gas of hydrogen, just protons. Forget about the electrons for right now. So if you have a bunch of protons running around in some gas, and you want to get them close enough together so that they become a nucleus, this strong force only engages when these protons become that close together. So they're repelling, and then they get close enough together, and then bam, they fuse together and form a nucleus. So how fast do they have to be traveling to be able to get that close together? Well, this fast, right? It's where, if you turn this around, that's where all of their potential energy of repelling is overwhelmed by the kinetic energy, right? Or another way to think about it is that their kinetic energy is used up by the potential. The closer and closer they get to each other, the more you use up that kinetic energy. So if they're traveling this fast, they can get close enough together to fuse. Well, that's kind of neat. Could that ever happen? What temperature of gas could that happen for? Remember that the temperature of a gas is just described by the average motion, the average kinetic energy, the average motion, the velocity of the particles in a gas. You might remember, just for kicks, I'll put it up here so it just looks different. Remember, we said that the average temperature back in Physics 1, the average speed of molecules in a gas or particles in a gas is 3 kT over m. So if here I know the speed, so what temperature does that correspond to? The temperature it corresponds to then would be like mv squared over 3k. And if you plug these numbers in, what temperature corresponds to a gas where the particles are moving at 10 to the 7th meters per second? It turns out that T is something like 5 times 10 to the 9th Kelvin, like 5 billion Kelvin. So this has to be a really, really hot gas for this to happen. But it could happen. Am I saying, for example, in the sun, this happens in the center of the sun, that the the hydrogen nuclei, the protons, come so close together because they're traveling so fast that they fuse. And that's what makes the sun shine. Am I saying that the center of the sun is 5 billion degrees? No, and the reason for that is, remember the way it goes is that there's some distribution of speeds, and this speed was the average speed of the molecules in the gas. You don't really need, for the sun to shine, you don't really need that many to be traveling that fast. All you need is for some percentage of them to be traveling that fast. So it turns out that the center of the sun is only about 15 million degrees. So 1.5 times 10 to the 7th Kelvin in the center of the sun. At that speed, or at that temperature, there's enough of the particles out here that are traveling fast enough so that you can get some fusion reactions. So anyway, that's kind of cool that just from considerations of potential energy of charges, we can get some insight as to how the sun works and how stars shine. So that's really neat.